So in this lecture, I will discuss the Cantor Set and function, and the Cantor function. So let's consider point x in the interval 0, 1. I will represent x in base 3, so x will be written as dot x1, x2, x3, and so on. And for that, I mean that I'm writing x as the sum for j larger or equal to 1 of xj divided by 3j. So here xj is an element of 0, 1, 2. And so when I write x as dot x1, x2, x3, what I'm meaning is that I'm representing x on the base 3, which is writing x in this way. Of course, there is some ambiguity in this notation, because if you take a point x1, xn, and assume that xn it's smaller than 2, and then you start with 2, so you fill with 2's to the end, this number x, which can be expressed in this way, can also be expressed as x1, x2, up to xn minus 1, and then xn plus 1, 0, 0, 0. So the same number may have two different expressions, and we just have to be careful when defining certain objects that these objects are well defined, so that they give the same result writing x in these two ways. So I leave it to you to check that these two numbers are equal, and therefore that the same number may have the different representations. Now I want to introduce the Cantor set, which is a compact subset of 0, 1. And this will be constructed by induction. So to define K1, let me first explain in a graph what I want to do, and then I will give you a precise definition. So let's consider the interval 0, 1. Let's divide the interval 0, 1 in 3 pieces. So this is 1/3, and this is the point 2/3. And in the first step, I will remove the open interval 1/3, 2/3. So K1 will be the union of these two closed intervals, the interval 0, 1/3, 2/3, 1. In the next step, I will just repeat the same procedure, but now applying this algorithm to each of these two intervals. So I'll divide each one in 3 intervals of the same length, and I will remove the middle interval, as I did in the first step. So this corresponds, well, this point here corresponds to the point 1/9, and that point to the point 2/9. That point corresponds to the point 7/9, and this one to the point 8/9. So what I'm doing is that I'm removing these two open intervals. So there are, at this second step, at the end of the second step, only 4 closed intervals remaining, and I repeat that procedure. In this way, at some point, I will have defined Kn, and the set K will be just the intersection for all n larger or equal to 1 of Kj. Note that these sets K are all compact. They are non-empty. It's a decreasing sequence of compact sets. Since they are all non-empty, the intersection is non-empty. So this is a non-empty set, which is compact. Now I want to define this set K rigorously. So for that, I will use this expansion of a point x in terms of its base 3 expansion. Well, let me define by 0. So that will be a subset of 0, 1. And what is this subset? Well, it's made of all points x in 0, 1, whose expansion starts with a 0. So point 0, x2, x3, and so on, which means that this is the sets of all x such that x1 is equal to 0. So what is this set? Well, if x can be represented by that, this means that I can write x as 0 over 3 plus a sum for j larger or equal to 2 of xj divided by 3 to the power j. This means that the interval 0, this set, is the sets which can be obtained by placing here for all sequence xj I can think of. So what are the points which I can obtain here? Well, this is 1/3 of j larger or equal to 1 of xj plus 1 divided by 3j. So you observe that here I can obtain what are the points which can be generated by this series. Well, these are exactly all points of the interval 0, 1. Therefore, this interval is nothing more than the interval 0, 1/3. Right? What I'm claiming here is that these sets, so the sets of all points x whose in the base 3 expansion the first digit is 0, it's exactly formed by the interval 0, 1/3. Because if the first digit is 0, x it's equal to 0 over 3 plus this sum, but this sum it's equal to that one, and by playing with the xj, I can, with this sum, generate at any point in 0, 1. Since I'm dividing that by 1/3, this is in fact the interval 0, 1/3, and therefore this set is the set 0, 1/3, which is exactly the first interval here. And in the same way, let me represent by bracket 2 the set of points x in 0, 1, such that in the expansion x1 it's equal to 2. So by a similar argument, if you take a point x whose first digit is equal to 2 in the base 3, x will be given by 2/3 plus by this computation 1/3 j larger or equal to 1 of xj plus 1 divided by 3j. Here I can generate at any point in 0, 1, and therefore the interval bracket 2 corresponds to the interval 2/3 plus the interval 0, 1 multiplied by 1/3, and this is the interval 2/3, 1, which is exactly the second set I obtained here. So K1 so my set K1 it's equal to the interval 0 union the interval 2, bracket 2. So in order to define K2, let me introduce bracket A1, A2. These will be the set of points x in 0, 1, such that in its base 3, x1 it's equal to A1, x2 it's equal to A2. And now what I claim is that K2 will be equal to the interval 0, 0, union 0, 2, union 2, 0, union 2, 2. Right? So just to convince you of this identity, let me see what is bracket 0, 2, what is the set bracket 0, 2. This is the set of points x in the interval 0, 1, such that in the expansion x1 is equal to 0, x2 it's equal to 2. So x it's equal to, in the expansion, the first digit is 0, so it's 0 divided by 3, which I will not write. Then 2 divided by 9. Then here I start with j equal to 3, and I have xj divided to power 3j. So I can rewrite that as 2 divided by 9 plus a sum. So let me take out 1 over 27. xj plus 2, 3j, and actually here I made a mistake. This is 9, I guess. So these sums, this series, you can generate it by playing with the digits xj plus 2, any number in the interval 0, 1. So this represents the interval 0, 1, which is divided by 1 over 9. So the set bracket 0, 2 corresponds to the interval 2 divided by 9 and then 3 divided by 9. Okay, which is exactly this interval over there. Right? So this second set corresponds to this second interval, the first one to the first interval, and we have here all 4 intervals. So you see that K1 is formed by all numbers whose expansion in base 3 started with a 0 or 2, while K2 will be formed by all numbers of the interval 0, 1 whose base 3 expansion starts with only the digits 0 and 2. So here are all possible combinations you can get with playing with the digits 0, 2. So in this way, and of course K1 contains K2. So in this way I can define Kn. So Kn will be formed by all points whose first n digits are either 0 or 2. So this is a union over all x1, or maybe let me call them a1 up to an, which belong to 0 or 2 of the sets a1, an, and where a1, an, it's equal to the points x in 0, 1, such that in the expansion, the jth digit xj, it's equal to aj for j between 1 and n. So it's clear that the sets Kn are decreasing, as we have seen that K2 is contained in K1, because here for Kn we are imposing a condition on the first n digits, while for Kn plus 1 we'll be imposing more restrictive restriction on a more restrictive condition on the number, since we will be asking that the first n plus 1 digits are either 0 or 1. So these are closed sets. They are decreasing, and so let me call K the intersection of all these Kn's. Whose definition is given here. As I said, well, these are closed sets. They are non-empty. Therefore, their intersection is non-empty. This is a property of the compact sets. So if you have a decreasing sequence of compact sets, which are all non-empty, you know that the intersection is non-empty. So K is a compact set, and what I claim is that the Lebesgue measure of K is equal to 0. That will be needed later on. So K1, it's the union of two intervals. So maybe let me represent by lambda of K1 the Lebesgue measure of this interval. So each interval has a length 1/3, and there are two of such intervals. So the Lebesgue measure of K1, it's 2, because there are two disjoint intervals, and each one has length 1/3. For K2, we have now how many intervals? Well, we have two digits, and we can choose each digit to be 0 or 2. So they have 2 to the power 2 sets. And each set now, where we are imposing a condition on the first two digits, so each bracket corresponds to an interval of length 1/n. So 1/3 to the square. So this is 2/3 to the square. So this is the Lebesgue measure of K2. And if you now consider the Lebesgue measure of Kn, again, how many sets there are? Well, we can choose A1, each of these digits, to be either 0 or 2, and there are n of them. So we have 2n, 2 to the power n possibilities. And for each fixed one, we're imposing a condition on the first n digits. So each of these brackets corresponds to an interval of length 1/3 to the nth, and therefore the Lebesgue measure of Kn is 2/3 to the n, and this is clearly decreasing to 0. And since K is contained in each of these sets Kn, the Lebesgue measure of K is equal to 0. So K, it's the Cantor, what's called the Cantor set. We just proved that the Lebesgue measure of the Cantor set is equal to 0. And now let me show that K is uncountable. Well, if you take a point x, what I claim is that x belongs to K if and only if x has a representation in which xj is equal to either 0 or 2. And of course, the points whose base 3 representation uses only digits 0 and 2, it's uncountable because you can make a correspondence with this set and the interval 0, 1 by taking here the binary expansion of the set and by dividing these two digits by 2. So let me first prove that a point x belongs to K if and only if it admits a representation which uses only the digits 0 and 2. So let's assume that x belongs to K. Well, if x belongs to K, then x belongs to Kn. And if x belongs to Kn, it belongs to one of these intervals. And if it belongs to one of these intervals, it means that, well, its first n digits are composed only by 0 and 2s. And therefore, this proves that xj belongs to 0 and 2 for all j. Because I can take here Kn as large as you want. And on the other hand, if you take a point x in the interval 0, 1, such that xj belongs to 0, 2 for all j, then it's clear that x belongs to Kn for any n, and therefore it belongs to an intersection, and intersection it's K. So this proves this claim that a point belongs, x in the interval 0, 1 belongs to the Cantor set if and only if it admits an expansion which uses only digits in 0 and 2. And now, let's observe that, well, I can define a function phi, which from k to 0, 1, and here I will send its expansion x1, x2, etc. to the point dot x1 divided by 2, x2 divided by 2, and so on. And this is 1 to 1. Since this set is uncountable, we get that the Cantor set is uncountable. So we have an example of an uncountable set whose Lebesgue measure is equal to 0. Right? So this is the Cantor set. And now I will define a function by using this construction. So in order to define this function, let me just introduce a new notation. En will be the interval 0, 1 minus the set Kn. So En, it's a finite union of open intervals. So E1 is the interval, the open interval 1/3, 2/3. Then E2, it's composed by these three intervals. So the interval 1, 9, 2, 9, open, 1/3, 2/3, and then 7, 9, 8, 9. This is E2, and so on. In general, En, it's the interval 0, 1 minus Kn, and this will appear later on when I define the set, the function I want to define. So let's just observe. So let me take E, which is 0, 1 minus K. And of course, well, E, since Kn is decreasing to K, this means that En is increasing to E. And lambda, the measure of the set E, it's the measure of 0, 1 minus the measure of K, but the measure of K is 0. So the measure of E, it's equal to 1. So the union of these sets En has measure equal to 1. Okay? So now let me define the, so now I want to discuss Cantor function. And the Cantor function is an example of a function which is monotone increasing. So I want to define a function f, from the interval 0, 1 to 0, 1, such that, well, it's monotone increasing, it's continuous, and we know that its derivative exists, and its derivative is equal to 0 almost everywhere. Okay. Well, it sounds, if you've never seen that before, it sounds a bit strange that we can find a function whose derivative is equal to 0 almost everywhere, which is continuous, and such that f0 is equal to 0 and f1 is equal to 1. So a function which is non-constant, increasing, monotone increasing, whose derivative is equal to 0 almost everywhere, and which is continuous. And I'm sorry, f1 equal to 1, I wrote. So let me draw a picture to explain how we will construct this function. So we want the function to be 1 at 1 and to be 0 at 0. And we will use the Cantor Set function in order to construct this function. So remember, when constructing the Cantor Set function, we first removed the interval 1/3, 2/3. So I want to define my function f in this interval. This corresponds to the first step. And how do I define this function? Well, this function is defined to its right at 1, and its value is equal to 1. To the left, it's defined at 0, and it's equal to 0. So I'll just take the average of these two values, which is 1/2, and I will define the function to be equal to 1/2 in this interval, which, remember, corresponds to the interval E1. And I will just repeat this procedure in the next steps. So in the next step, I was removing the middle interval of the two remaining intervals, closed intervals that we have. So how now in the second step we will define the function in these two intervals. How do we define? Well, if you go to the right, this function takes the value 1. To the left, it takes the value 1/2. So the average is 3/4. So we will define in this interval the function to be 3/4. And the same way here, the average is 1/4. So we'll define the function in these two sets to be 1/4 in the first interval and 3/4 in the second interval, and so on. And in this way, we'll construct a function. And note that this function is such that its derivative is equal to 0 on the set En. So remember that the set En was the complement of the nth step of the construction of the Cantor set, so it was the union of these intervals. Well, on each of these intervals, the function is defined to be constant, so f prime is equal to 0 in each of these intervals, so it will be equal to 0 in the union of these intervals, but this is my set E, and we have shown that the set E has full measure, so it has measure equal to 1, and therefore, if we succeed to prove that this function is continuous, we will have an example of a function which is continuous and whose derivative is equal to 0 almost everywhere. So this is an informal presentation of that function, and now I will define it with all details. And for that, I will use again the expansion of a number in base 3. So remember, I have x, which is point x1, x2, x3, and so on, where each of these xj belongs to 0, 1, 2. Given that point, let me define nx. Nx will be the minimum over all j such that xj is equal to 1. And if this set is empty, so if xj uses only all xj belongs to 0, 2, so this set is empty, so I'll say that the minimum of an empty set is just equal to plus infinity. And here I have to be careful because, well, n of x is not really well defined because the same point can have two representations. So remember that a point 1 say 2, 2, and so on. Let me call x this point. So nx, according to my definition, nx will be equal to 1. But I can also represent nx by dot 2, 0, 0, 0. And in this case, nx, it's equal to plus infinity. Right? So whenever I use an x in a definition, I have to be careful to show that the object I'm defining is well defined. And I want to use an x to define the function. So here's the definition of my function. I take a point x, and what I will do, I will sum 1 over 2 to the power j, j from 1 up to nx, but I will sum only those j's for which xj it's either 1 or 2. And this sum it's equal to, it's a sum from 1 to plus infinity if xj it's either 0 or 2 for all j. Right? Because in that case, nx will be equal to plus infinity. As I said, nx it's not well defined. It depends on the representation we use. Let's check that it doesn't, well, the definition of f doesn't depend on that representation. So the ambiguity comes from a point, x1, xn, which from one index up, all the digits are 2. And of course, let me assume that xn is different from 2, so xn it's 1 or 0. So we have that possible representation for a point, but we have an alternative representation which is x1, xn minus 1, xn plus 1, 0, 0, 0. Right? These 2 points are the same. And let me check that if I compute f by using this representation, I get the same result that I get using that representation. So by the first representation, well, let's observe the first n minus 1 points. The first n minus 1 points are equal in this representation. So if one of these digits is equal to 1, then the two representations coincide because n of x is equal in both representations, right? So if x1, if there exists a j, or if you want to see if 1 belongs to x1, xn minus 1, then f of x, f it's equal either using that representation or that representation. So now let's assume that 1 does not belong to x1, xn minus 1, so I have here only 0 digits. And there are two possibilities, either xn is equal to 0 or xn is equal to 1. So let's consider the first case in which xn it's equal to 0. In that case, by using the first representation, fx it's equal to the sum from 1 up to n minus 1. all these digits are 0, 2. Okay, so this is 1 over 2j, 1 if xj it's equal to 2. Why? Because it's not equal to 1. We assume that. We assume that 1 doesn't belong. So to be larger or equal to 1 is the same as to be equal to 2. Then I have xn, which is 0. So that term 2 to the power n does not appear. And then we have 2. And you observe that in this representation, nx it's equal to plus infinity. So I have a sum for j larger than n plus 1. They are all equal to 2. So this is just 1 over 2j to the power j. And this sum, it's equal to 1 to the power 1 divided by 2 to the power n. So fx, it's equal to that expression plus 1 over 2n by using the first representation. Then let's compute f by using the second representation, which is this one. I have first the contribution of the first n minus 1 digits. This is the sum from 1 up to n minus 1 of 1 divided by 2 to the power j. They are all different from 1. So I can also write xj equal to 2. Then xn plus 1 is equal to 1. So in this case, nx it's equal to n. Therefore, I have to stop at n. And I get a contribution 1 over 2n. And you observe that these two expressions are equal. So fx takes the same value if we either use that representation of x or this representation of x. Well, we proved that in the case in which xn is equal to 0. So now let's see what happens if xn is equal to 1. So if xn, and I will write in red just to avoid repeating everything I wrote. So let's assume now that xn is equal to 1. And let's consider the first representation. So in that case, I have the contribution of the first n minus 1 terms. They are all different from 1 by assumption. And then xn is equal to 1. So according to this definition, I have to stop at n. And I get a contribution 1 over 2n because xn is equal to 1. So again, f of x is given by this expression. Now let's see what we get for the second representation. So fx, there is the first contribution of the n minus 1 first terms, which is written here. xn plus 1, it's equal to 2 now, and all the other digits are 0. So in this representation, I get that nx is equal to plus infinity, so I have to sum everything up to plus infinity. For the digit n, xn is equal to 1, so xn plus 1 is equal to 2. So this is larger or equal than 1, and therefore I get a contribution 1 over 2n, which is written here. And for all the other digits, they are all equal to 0, so I'm not counting them because they are equal to 0. So here, again, it's the value of fx by using this second representation. And again, we have that both representations give the same value, and therefore that f of x is well defined. So this proves that this function is well defined, though n of x is not well defined. Okay. Now, I want to prove all the properties which were listed here. So the first property was that f is monotone increasing. So let's prove that f is indeed monotone increasing. Let me take x less or equal than y, or strictly smaller than y, and I want to prove that f of x is less or equal than f of y. So let's write x1, x2, x3, and so on. For x, the same thing for y, y1, y2, y3, and so on. And let me define m as the last digit for which they are equal. So let's assume that the first m digits coincide and the next one is different. If x has to be smaller than y, this means that this digit, xm plus 1, it's smaller than the digit ym plus 1. Right? I'm assuming now that x1 is equal to y1, x2 equal to y2, up to xm, which is equal to ym, but that these two are different. And since they are different and x is smaller than y, xm plus 1 has to be smaller than ym plus 1. Okay? If xm plus 1 was larger than ym plus 1, you could check that in the worst case, they would be equal. Okay? That might happen if you have, for instance, 1 and 0. Say that now you extend with 2's, here with 0's. These two, so this is the worst case, possible case, but in this case they are equal, and I'm assuming that they are different. So if they are different, we need to have that xm plus 1 is smaller than ym plus 1. Okay, so if I wasn't clear, please check that we necessarily have that xm plus 1 is smaller than ym plus 1. Now let's compute fx and fy. Well, again, we have several cases. If there is a 1, if one of these digits is equal to 1, then by the formula for f of x is equal to f of y, and there is nothing to prove. We have an identity here. So I can assume that all these digits are different from 1. They are either 0 or 2. In this case, f of x, it's given by, well, the contribution of the first m terms, which I will not write. I will call that maybe I. So maybe I write it just to make sure that you're following. So I will be the sum from 1 up to m. So remember, I'm assuming that it's different from 1. So n of x, it's larger or equal than m plus 1. I will be xj divided by 2j, 1 divided by 2j if xj is larger than 1. Actually equal to 2, since I'm assuming that they are different than from 1. So f of x, it's the contribution of the first m terms. And then I have to consider a different case. So first assume that xm plus 1 is 0 and ym plus 1 is 1. So what are the cases? Well, I can have here 0, 2, or 1 and 2. So I have to consider these three cases. So let's first assume that xm plus 1 is 0 and ym plus 1 is 1. So in this sum, n of x, it's larger than m plus 1. So here I have plus, but my sum starts from m plus 2, because the contribution of the digit xm plus 1 is 0, because xm plus 1 is equal to 0. So I have here a sum from starting at n plus 2 of xj of 1 divided by 2 to the power j if xj is larger than 1 and up to nx. Of course, this is bounded by 1I plus, well, in the best possible case, all these digits are larger than 1, and x is equal to plus infinity, so I have a sum starting from n plus 2, so this gives me a contribution 2 to the power n plus 1. So fx, it's bounded by this quantity, and let's see what we know about fy. Fy, well, the first contribution of the m terms, it's equal to the first contribution of the first m terms for x, because they coincide, and this I call I. And then I have ym plus 1 is 1. So here I stop my sum at m plus 1, because ny it's m plus 1. Ym plus 1 it's equal to 1, so this gives me that contribution, which is, so this gives me the contribution 2 to the power m plus 1, and so you see that this quantity, it's indeed, well, this quantity is equal to that one, and therefore f of x is smaller or equal than f of y. So we proved the inequality in the first case. So now let's consider the second case. In the second case, f of x did not change, because I'm assuming still that xm plus 1 is 0. So here is a bound for f of x. While for y, I'm assuming that ym plus 1 is 2. So if ym plus 1 is 2, this means that n of x is at least m plus 2. And since ym plus 1 is 2, I'm taking, well, the contribution for j equal to m plus 1, it's 1 divided by 2 to the power m plus 1, which is here. So in this case, instead of an identity, what I have is that I have an inequality. So fy it's larger than that, because you might have a contribution for the term m plus 2 and so on. But we still have that f of x, it's less or equal than f of y in this case. So we checked in the case 0, 2, and now it remains to check the case 1, 2. In the case 1, 2, f of x it's still equal to I plus this expression. But now n of x it's equal to m plus 1. So for this last case, f of x it's actually equal to this sum, I plus 1 divided by 2 to the power m plus 1. While f of y, so it's equal to 2, we compute already the value. We proved that in this case, in the case in which ym plus 1 is equal to 2, we have that f of y it's larger or equal than this expression, and therefore we still have that f of x it's less or equal than f of y, and therefore even in that case we know that f of x it's less or equal than f of y, which proves that f it's monotone increasing. So this is one assertion. I don't want to erase maybe all, well, at least the definition of f of x. And so now I would like to prove that f is continuous. And to prove that f is continuous, what we will prove is the following. So this is a first step in order to prove that f is continuous. Let's take point x smaller than y. And let's assume that y minus x, it's bounded, strictly bounded by 1 to the power 3n. So let's assume that y minus x, it's bounded, strictly bounded by 1 divided by 3 to the power n for some integer n. And what I claim is that f of y minus f of x, it's less or equal than 1 to the power 2n. So this is what I want to prove now. And maybe let me write here the definition of fx. Fine, so let's assume that this holds. Let me write x as dot x1, x2, xm, y, y1, y2, ym. Let's assume that x1 it's equal to y1, x2 equal to y2, xm equal to ym. So this is, and that xm plus 1, it's smaller than ym. Here again I'm assuming that x is smaller than y. So m plus 1 will be the first index for which they are different. And we have seen that in this case we need xm plus 1 to be smaller than ym plus 1. But let's see what this assumption tells us. We know that y minus x is smaller than 1 over 3n. So this will give us some information about m and n. So first, assume that m it's larger than n. Maybe larger or equal, I'll see that in a second. So if m it's larger than n, this means that these first, well, we know that all these expressions are equal. So let's compute the difference between fy and fx. Well, maybe there is a 1. Maybe one of these digits is 1. In this case, fy is equal to fx, because all these digits are equal. xj is equal to yj. So if there is a digit 1 here inside, these two expressions are equal. So I can assume that y1 does not belong to x1, xm. Okay, so let me repeat the argument. If 1 belongs to this set x1, xm, then n of x is equal to n of y, and therefore, and it's smaller than m, and therefore f of x is equal to fy, and therefore we have this inequality, so there is nothing to prove. So I can assume now, I can consider the only case of interest is the case in which 1 does not belong to x1, xm. If 1 doesn't belong to f1, fx, 1m, well, fy minus fx, there will be a contribution of the first m terms, but they cancel because they are equal. So fy minus fx will be equal to the sum starting from m plus 1 up to ny of 1 over 2j yj larger or equal than 1 minus well, but we can bound this expression by taking the worst case in the first term. The worst case would be ny equal to plus infinity, and that all the yj's are larger or equal than 1, or equal to 2, say, and this will give us a contribution of 2n. While in this term, well, it's negative, so we get a bound, and this shows that fy, I'm sorry, here it's m, fy minus fx would be bounded by 1 divided 2 to the power m. So if m is larger or equal to n, this is less or equal than 2 to the power n, and we have proved. So this simple computation shows that if m is larger or equal than n, fy minus fx it's indeed less or equal than 1 to the power 2n. So the only difficult case is the case in which m is smaller than n. So now I will consider the case in which m is strictly smaller than n. Well, so here's, so this is position m plus 1, this is position n, and what I claim is that if the difference between y and x is smaller than 1 to the power 3n, then and xm plus 1 is smaller than ym plus 1, I have at the positions m plus 2 up to the position n only 2's for x and only 0's for y, and xm plus 1 it's equal to ym plus 1 minus 1. Okay? So let me state that more clearly. So I know that xm plus 1 it's bounded by ym plus 1. So let's assume there are 3 cases again. Either we have 0, 1, 1, 2, or 0, 2. So I have to consider separately each of these cases. So let's consider first the case in which xm plus 1 is equal to 0 and ym plus 1 is equal to 1. So I know that 1/3, 1 over 3 to the power n, by assumption, it's larger than y minus x. But y minus x, express them in base 3. So the first m terms will cancel. Then I have here the contribution of the digits m plus 1, but the digit ym it's 1 and 0, and the digit for x is 0. So this gives me 1 divided by 3 to the power m plus 1. And then I have the sum starting from m plus 2 of yj and minus the contribution starting from m plus 2 of xj. Okay. The contributions up to m cancel. The contribution at m plus 1, it's 1 due to ym and 0 due to xm, and then we have the contributions starting m plus 2. So this is an identity. Now I want to bound that from below, and I will say, well, let me just forget about these yj, and let me write this expression 1 to the power 1 divided by 3 to the power m plus 2 as the sum starting from n plus 2 of 1, 3j. So you see that this term is equal to that one, and we have here this term, which is minus, and I'm sorry here it's not 3j, but it's 2. Okay. So I leave it to you to check that this sum it's equal to that one. This is telling me that if you start a point with only digits 2, it's equal to the point in which you start one digit before with a 1 and everything else 0, which is this term here. So I rewrote this term in this way. This one I said, well, that it's non-negative. And for that one, I just write it back. So here what I get is 2. I'm starting from n plus 2. And what I have is 2 minus xj divided by 3 to the power j. And now what I observe is that, well, I need this sum to be bounded by 1 over 3n. So if xj, if there exists an xj, if xj is different from 2, for j in between n plus 2 and n, minus n minus 1, this inequality is false, right? Because I will have here a number divided by 3j, which is smaller than 3n. And actually, I can go up to n, because this inequality is strict. This is why I chose here a strict inequality. If I go up to n, so if here xn is not equal to 2, I have here a contribution which is either 2 to the power 3n or 1 to the power 3n, and that strict inequality here will be false. So again, I'm claiming that it follows from this strict inequality that xj has to be equal to 2 for j between n plus 2 and n, because if one of these xj's it's either 0 or 1, I have here 2 or 1 divided by 3j's, which is larger or equal than 1 over 3 to the n, and that would give me a contradiction. So this proves that in this case, all these digits, they have to be equal to 2 in order to satisfy that strict inequality. So this is case 1. So now let's see the second case. So that's case 1. Now let's see case 2. Case 2, I have that xn plus 1 it's 1 and yn plus 1 it's 2. And now I claim that I have only zeros to the right of yn plus 1 up to n. And the reason it's similar well, let's write again y minus x. Y minus x, the contribution of the first m terms, they vanish. So y, it's, let's start at m plus 1. I have a 2. Then I have this sum. And for x, now x it's equal to 1, so minus 1 to the 3m plus 1 minus this contribution starting from m plus 2. And if you take out one of these two, I get one. So this is the difference, and now I want an inequality. So this expression, it's less or equal than the case in which all xj are equal to 2. If all xj are equal to 2, this sum will give me 1 over 3 to the power m plus 1. So this sum, it's bounded by 1 divided by 3 to the power m plus 1. So I have here this expression, it's bounded below by this sum minus that expression, so this will cancel with that one, and what I get is that that expression, it's actually bounded below by the sum starting from m plus 2 of yj divided by 3j. And here again, I can argue as before, saying that, well, if one of these yj, it's 1 or 2 for j between m plus 2 and n, this strictly inequality cannot be satisfied. Okay? If yj is equal to 1 or 2 for 1j between m plus 2 and n, this inequality is false, and this proves that all these index here, they have to be equal to 0 in this second case. And finally, I claim, so this is the second case, and finally I claim that in the third case it's impossible because this inequality won't be satisfied. So let me now assume that xm plus 1 is 0, ym plus 1 is 2, and let me show that this is not possible because here I'm assuming that m is larger than n. So let's repeat the computation for this third example. Let's compute y minus x. The first m contribution will vanish. Now for y, I have ym plus 1, which is equal to 2. Then yj starting from m plus 2 minus x. The contribution at m plus 1 is 0. And then I have the contribution starting at m plus 2. I want to bound that from below. So this expression here, it's positive. Let me keep 2 divided by 3m plus 1. So this expression, it's positive. So this term, it's bounded below by this one if I just neglect that one. xj, this expression, as I did in the previous step, this is bounded by the case in which xj is equal to 2 for all j. And that will give me 1, 3 to the power m plus 1. So this expression is bounded by this. With the minus sign, I get a lower bound with minus 1, 3m plus 1. So this gives me a 1 divided by 3 to the power m plus 1, right? And therefore, I can't have, well, and this is wrong because m is strictly smaller than n, so m plus 1 it's smaller or equal, and therefore I can't have, so this expression, it's less or greater or equal, to that one, so it can't be smaller, strictly smaller than that one. So this case, it's impossible, and I can, because in that case, it won't be true that y minus x is bounded by 3n. So I can restrict my attention to these two cases, and I have to prove in these two cases that fy minus fx is less or equal than 1 to the power 2n. But now it's very easy. Okay, once we observed this fact, it's very easy to obtain that bound. It's enough to just recall the definition of Fy. So again, Fy minus Fx, I can just forget about the contribution of the first m terms because they are equal. So Fy, let's consider the case 1. In case 1, x Fy ym plus 1, it's 1. So these sum stops at m plus 1. And it gives me a contribution of 1 to m plus 1. So this is the contribution of Fy, because we stop at m plus 1. And then minus Fx. The contribution of Fx, well, these ones were cancelled with dy. So I have to look at the contribution of xm plus 1 starting from the digit m plus 1. But this one, it's 0. So that contribution doesn't appear. And now I have 2. And these 2, it's going at least from m plus 2 to n. Okay, all x are equal to 2. So I can count all these contributions from m plus 2 up to n. Since I'm assuming that 1 doesn't belong, so I'm taking, so the n of x, it's larger than n. And here I still have the contribution from n plus 1 up to n of x of this expression. Okay? But this is less or equal. Then let me neglect this expression. 2m plus 1, let me write it as the sum of 1 over 2j starting from m plus 2 minus the sum of 1 over 2j from m plus 2 up to n. So you see that these will cancel, the contribution up to n will cancel, and this will give me a sum starting from n plus 1 of 1 over 2j, and this is exactly 1 over 2n. So that proves this, the inequality in the case C1. So this is a quite long computation, but actually a very simple one. Right? We have to be careful by considering all cases. Now let's consider the case C2. In the case C2, xm plus 1, it's 1, ym plus 2, ym plus 1, it's 2. So again, let's write Fy minus Fx. Fy has a contribution of the first m digits, but these ones will cancel with the contribution of x, so I don't count them. Then we arrive at ym plus 2. This gives me a 2, so there is a 1, 2m plus 1 coming from the contribution of ym plus 1, which is a 2, so I have to continue, but then I have zeros. So the zeros will not appear because I have this condition requiring the digit to be at least 1. And then maybe I have a further contribution starting from n plus 1. So this starts from n plus 1 of 1 to j if yj it's larger or equal than 1. And this goes up to n of y. Then minus f of x. So I'm not counting the contribution of the first terms. And here I get that xm plus 1, well, it's 1. So nx, it's m plus 1. I have to stop. And this gives me a contribution of minus 2m plus 1. So these two terms, they cancel. This difference, it's bounded by this difference. If I neglect this condition, and if I sum up to infinity, but this sum, it's bounded by 1 over 2n, because I'm starting from n plus 1, and this again proves this inequality. So we have proved that if y minus x is bounded by 1 divided by 3 to the power n, fy minus fx is bounded by 1 over 2n, and with that we will be able to prove the continuity of my function f. Actually, we will prove something slightly stronger. We'll show that f is Holder continuous. So now fix 0 x y less than 1. Consider the y minus x. And now let's consider n. So you see this is small. So I'm taking n, and as n increases to infinity, this is getting smaller and smaller. So maybe there exists 1 such that 1 over 3n and 1 over 3n plus 1. Okay, so there exists n larger or equal than 0, because we know that y minus x should be smaller than 1. So maybe let me take out y just to guarantee that y minus x now it's smaller than 1. Therefore, this inequality holds for n equal to 0. So now I can find 1n such that, well, this is smaller than 1 over 3n, but it's larger than 1 to the power 3n plus 1. And maybe let me put I'll put less or equal. I'll get it back here. And so let me repeat. I'm assuming that I'm taking y larger than x, both points between 0 and 1. And what I claim is that I can find n larger or equal to 0 for which this inequality holds. Right? Y minus x, it's smaller than 1. This is the case if n is equal to 0. This is 1. So if n plus 1, if 1, this is larger than 1/3, it's fine. If it's not, well, take it here, and then you can find n for which this inequality holds. So now let me rewrite that inequality as 3n less or equal than 1 divided by 1 minus x smaller than 3n plus 1. Let me take a logarithm on both sides and say that, well, n it's less or equal than the logarithm of 1 divided by y minus x divided by log 3, and this is smaller than n plus 1. So the n which satisfies this inequality satisfies this one. Now I know that since y minus x is bounded by 1 over 1 divided by 3n, I know that fy minus fx, which is positive because f it's monotone increasing and I'm taking y larger than x. According to this, this is bounded by 1 to the 2n. So let me rewrite 1 to the 2n as, let me take exponential and logarithm. So this is bounded by exponential n times the logarithm of 2. Now I want to bound this expression. So to bound this expression, I need a lower bound for n, and the lower bound is given here. So n it's larger than this expression, which is log 1 y minus x log 3 minus 1. And let me replace, therefore, n by this expression. So this is less or equal than 1 exponential. I'm replacing n by this expression here. So I have log 2, which is multiplying log of 1 divided by 1 minus x divided by log 3 minus 1. So that will give me a log 2 with a minus. The exponential of log 2, it's 2 with a minus 1 over 2, so this is equal to 2. Then I have the exponential of the same expression without this minus 1. So I get, let me put log 2 divided by log 3 as a constant, put it inside this logarithm. The logarithm will cancel with the exponential, and what will remain? It's 1 over y minus x to the power log 2 over log 3. And so, and this is equal to 2 times y minus x log 2 divided by log 3. So what did we prove? We proved that fy minus fx so if you take y minus x between 0 and 1, y larger than x, what we get is that fy minus fx it's less or equal than 2 times y minus x to the power log 2 log 3. So that proves that f is, well, wholer continuous with a coefficient given by log 2 divided by log 3. And in particular, my function f is continuous. So that proves the continuity of my function f. We have seen that f is monotone increasing, and let me remind that f it's constant on the intervals ej. So ej, here you have to remember that ej was given by 0, 1 minus kj, or let me, instead of j, use n. Kn were the union of x1, xn in 0, 1 of the intervals x1, xn. Right? And x1, xn were the sets of x such that, and again let me use that a1, an so a1, an were the points x for which xj it's equal to aj, j between 1 and n. So what is the set En? Well, the set En, it's formed by all the points at which a 1 appears. So An will be, well, either you have a digit 1 in the first, and let me take, well, these are closed interval, so let me take the open intervals, because these were the definition of my En. So you take all points whose first digit is equal to 1, and you take the interior points of that. Or you start with a 0, and then you get a 1. Or you start with a 0, 2, and then you get a 1. and so on. So in all these intervals, you go up to the last one, which are points in which you have b1 up to bn minus 1 and 1, where b1, bn minus 1 belong to 0, 2. So these are my, so this is how you write your set En. So I leave to you to check that the set En can be represented in terms of these expansion as these sets. So all points whose first digit it's a 1, all points whose first digit is a 0 or a 2 and then a 1, all points with the first n minus 1 digits are 0, 2s and then a 1. And I want to prove that f is constant on En. So I have to show that f is constant in a set as this one. So let's take a point x and a point y, a point x in this set b1, bn. Minus 1, 1. b1, bn minus 1 are different from 1. So all bj's are different from 1, so they are either 0 or 2. So if you take a point in this set and you look at here, well, nx it's equal to n, so that fx will be equal to the sum from 1 up to n minus 1 of 1 over 2j. Here I will sum only the j's for which bj is equal to 2, and plus the last one, which is 1, therefore I have a 1 over 2n. And you see that this expression doesn't depend on x, it depends only on the bj's. So f it's indeed constant in this set, therefore it's constant on En. If f is constant on En, this means that f prime, so En it's made of open intervals, this means that f prime is equal to 0 on En. Well, and this is true for any n, so f prime is equal to 0 in the union over all En, and this is my set E. So we proved that f prime is equal to 0 on my set E, and the measure, remember, the measure of my set E, it's equal to 1. So f prime, it's indeed equal to 0 almost everywhere, and that proves that the function given by this expression, it's monotone increasing, it is continuous, and its derivative it's equal to 0 almost everywhere. And that completes this lecture.